Hi, I'm Dr. David Hudson, and this is part 3 of the first lecture for Introduction to Marine Science for the Non-Scientist. So in this section, we're going to talk about the bit that's now over this reef. So we're going to talk about the properties of water and global circulation. The fact that when we search for new planets to see if there is life on a new planet, that we look first for water, tells you something about its properties. It's a really unique molecule, and it helps with the circulation of the movement of heat around the world. So just to delve into a few things, a few major concepts that are, if you're in marine biology, you typically think quite a bit about thermoclines and salinity and the density across the world because it affects how water moves even at small spatial scales. But let's just delve into it for a minute. So first of all, when we think about the density of salt water, the molecules in water that are at around 75 degrees Fahrenheit or mid-20s centigrade are going to move around quite a bit more than they will at around 4 degrees centigrade or down to even 32 degrees Fahrenheit. So cold tends to be more dense. So if we look at the density here, as you increase in depth, you're noticing that there's a difference in the spatial places where you find these differences. So if we think about a place where the water temperature is around 4 degrees centigrade, that's also going to be its densest per cubic centimeter, or cc. So you're going to have a denser packing of molecules in the deeper depths. That makes sense. That means deep water and cold water sinks. Now, that's a really important concept because if you think about where we have colder water and higher density, we're going to think about places in the world where water would typically be sinking. Now, temperature, when it comes to temperature, water has very high heat capacity, so it can store quite a bit of heat. And since animals that are there are not subject, therefore, to big fluctuations in temperature, they can survive and not have to put a lot of energy into dealing with temperature. This is a problem if you have stochastic events where you have a big spike in temperature, because those animals will not be able to deal with that often. The other big piece here is, when we think about salinity. So salinity will vary at the surface. Obviously, you've got some things that could affect salinity. Certainly, freshwater runoff from streams, in and around rivers, you can be pretty far. If there's still tidal influence, you can still be down to 15 or 5 even parts per thousand. So typically, though, the full strength salinity is somewhere between 33 and 37 parts per thousand. There are other places in the world where you end up getting some estuaries that get shut off and the salinity spikes that can be at up to 60 or more. Obviously, there are extremophiles that can live in those situations. The Great Salt Lake is an example of a place that has very high salinity. You have brine shrimp that are produced for feeders for fishes all around the world. But those places are extreme, and they end up with fewer animals and plants that are able to deal with those conditions. So the point here is that you see around 1,000 meters a leveling off of the conditions within the ocean, and things become quite stable along salinity lines, temperature, and density. If we were to think about the seasonal impacts and the locational impacts of just zooming in on temperature, for instance, if we look at the surface in the tropics, you're going to see a very much high temperature at the surface layer. As you go down to around 200 meters, things start to taper off onto the normal deep water temperature around 4 degrees centigrade. So this trajectory here is where we would see for a depth profile for temperature in the tropics. In the temperate zones, you would typically see this be a little bit less pronounced. Surface areas would be around 11 degrees. There is a seasonal impact we'll talk about in a second. And then in the polar regions, you typically have around 4 degrees on the surface, and then it tapers off and it goes pretty constant all the way down. Now, if we think about the temperate zones, you actually have a variation based on season. Remember, we're back to how the number of photons from the sun that hit the Earth on a spherical surface, right? So if you have more per square centimeter, that's going to be the tropical zones. They're always pretty much hitting at 90 degrees, so you just end up with more photons, more energy hitting per unit area in those areas than you do in other areas of the globe. The reason why we get the seasons, which we'll talk about in a second, is that varies in the temperate zone and the polar zone based on the angle of the Earth and how that's rotating around the sun. So when it's closer to 90 degrees, you end up getting more energy, and when it's further from 90 degrees, you get less energy per square centimeter. That's the main driver behind seasons. So in the summer, we get a very pronounced thermocline in the summertime, where surface temperatures around 22, 23 degrees centigrade in the temperate zone. And those will taper down to the permanent kind of main thermocline, where we get down to those same deep water temperatures. And in the wintertime, you end up with this, again, 11 degrees on the surface down to our normal temperatures in the deep water. So as we're thinking about light, and we're starting to get into this concept of, okay, there's a different amount of light hitting different parts of the surface of the Earth at different times of the year. Certain areas are going to get more light all year round. Now, as we go down in the ocean, the different spectra of light, the different wavelengths of light that make up the light from the sun start to peel out. So that what we perceive as different colors are actually different wavelengths of light. We typically will see a complete attenuation at depth. This means that if you've got photosynthesis happening, the best photosynthesis is happening closest to the surface, where the most energy and the most variety of wavelengths are available. But we typically lose our reds and oranges first as we go down to about 33 feet. And you can notice this if you're a diver. I've seen people bring their flashlights on in the daytime dives so that they can see the reds and the oranges when they get down to a 60-foot depth range. You can see those colors again. It's also why in the deep sea, animals often end up being red or orange, because there is no red or orange wavelength down there, so it essentially shows up as black. It's really quite interesting. We'll talk about that in a later lecture. You then typically will use your yellows and your violets at around 30 meters, just before 30 meters, about 100 feet in depth. And then your greens and your blues are the last to go. At around 60 meters depth, you end up starting to see some blues gone. Now, when we're thinking about the consequences of this, again, a lot of it's around photosynthesis, and a lot of it's around the amount of energy that's available. And if you've got photosynthesis happening in the top part of the ocean, remember you have decomposition that's happening below in all those places. But if the balance is more photosynthesis to less decomposition, you end up with a net positive production. So that's going to be important later when we start to talk about the oxygen minimum zone and some of these other concepts a little bit later. Thinking about as you go down, there's also the effect of these molecules on top of you. So if you're a diver, if you were to take down a balloon and go to 33 feet of depth, that balloon would be half of its size. So the point of this is that right now when we're sitting at our desks, a whole atmosphere of pressure is sitting on top of us. That's the entire atmosphere. But if we go 33 feet down, 10 meters down in the ocean, there's another whole atmosphere worth of pressure on us. And then every 33 feet after that, there's another whole atmosphere. The pressure continues to go up, go up, go up, and this is why submarines and submersibles have to be designed to withstand these pressures And if one is going to do commercial diving or extreme deep diving, the equipment gets different as you go down because we have these nice soft bodies that end up getting crushed otherwise. The other piece that comes into play is the fact that if you are a diver, you have to think about the different gas laws and the fact that as you are at 30 meters, you're actually breathing in way more molecules of air than you normally would at the surface. That is dissolving in your blood, and if you go up too fast, you don't breathe that off in time. And you can get sick or have a worse consequence. So the fact that this pressure is in place means that animals and other organisms have to adapt to the pressures. Moving on from that, remember we've got this spherical Earth that we live on, and yes, it's spherical and it's moving around the sun, but it also rotates. So because it rotates, this creates the Coriolis effect. So if you were to try to start at the North Pole and fly directly to the equator, your trajectory, because the Earth is spinning underneath you, would actually be deflected to the right. Same thing if you were trying to fly from McMurdo Station in Antarctica and try to fly directly north, you actually have to compensate by because you're deflected to the left. So this is really important for the direction of hurricanes spinning, the direction that you have to compensate in a boat or in a plane. This actually affects how fast you can create a world record. If you want to be if you're a rower and you want to create more of a world record, you need to get closer to the equator, because over the course of a longer distance race, even 2,000 meters, you're going to be correcting a little bit for Coriolis, which is really important because it can be as much as 7 or 10% of your energy expenditure. So if you're trying to set world records, this air and water circulation piece is really quite important. I mentioned a little bit earlier that there's unequal heating around the Earth. So if we think about the sun being over here to the right and rays that are hitting the equator are hitting around 90 degrees, we get the most energy per square centimeter in the equatorial region. Now, as we get further up, you're hitting at an angle, so there are fewer rays per square centimeter, just because it's hitting it's hitting a curved surface. And because the Earth is tilted, that's different at different times of the year because it's going around the sun at these different angles, at the same angle, but the sun will hit at a different angle. Now, what this does is it means there's just far more energy getting to the equatorial regions, and that heats air, it rises, and cooler air comes in from the polar regions and replaces it. That's wind. Now, this is an idealized model, but so it's far more complex in real life. But this Coriolis effect then acts on this, and we end up with the gyres that we'll talk about in a second. So if we're thinking about the different seasons for this, we've got the sun over here to the right. In a northern winter, we get fewer rays per square centimeter, and this would be a high density of incident rays in the southern summer. And the Earth is rotating around the sun at that same angle. So it's literally where you are in space around the sun. When we think of how this ends up creating wind patterns, well, we've got this rise that's happening in the equatorial region. There's then cooler air that comes in. Cooler could still be 30 degrees centigrade. It could still be quite warm to our perception, but it's cooler than the air that's heating at 50 degrees centigrade here at the equator. That's going to then go into the high altitudes and cool down and sink. Again, this is about densities, so as you heat anything up, it's density decreases. As you cool it down, its density increases because the molecules are getting closer together. Now we end up with a couple of things that end up happening once the Earth turns under this, and we end up getting, again, deflection to the right. Here, if you kind of turn your head and look at this arrow, the northeasterly trade winds that are coming from the northeast and going to the southwest are moving toward the intertropical convergence zone. The southeasterly trade winds, again, will deflect to the left in the southern hemisphere, are moving to the left for the same reason. So when the air is coming in, yes, it would like to move up this way, directly north or directly south, but because the Earth then turns, it gets deflected. So what ends up happening in the next higher latitude, we end up getting another Hadley cell that is going to cycle up in the northern latitudes, and we'll get westerlies. So mariners are able to use these different wind routes and wind patterns to navigate around the world and to get to new places. So commerce has been driven by this over time too. So we've got this combined. When we get the combined effect of both the Coriolis effect and these unequal heating, we end up getting this circular cycling around the world, and we get these different gyres, which we'll talk about in a second. Related to this, and related to the deflection around the Earth's surface, we have the effect of wind on the surface of water. And now, remember, there's friction when you have molecules interacting, and so when wind blows on the surface of the water, the surface current is around 45 degrees from that. But in what was described by Ekman, the Ekman spiral, those molecules are deflected by 45 degrees, but then so are the water molecules underneath, and so are the water molecules under those water molecules. So you end up with a net transport of water in the northern hemisphere to the right, in the southern hemisphere. So you get this essentially you get this deflection off into the directly 90 degrees to the wind pattern. So what this presents is, as you figure you've got these northeasterly trade winds here to the around the Canary Islands, you end up with a net transport of this equatorial current toward the Caribbean off of Africa. During hurricane season, this is the current that brings hurricanes with it. As you're moving upward, you've got the Gulf Stream. So again, you're in the northern hemisphere, so this is moving up, and it moves offshore to the right. So everything moves to the right in the northern hemisphere. So the Coriolis effect affects these currents as well. If we now look at the Peru current, which is a cold water current off of South America, that current comes up on the western side of South America, but because we're in the southern hemisphere, the Ekman transport is to the left. So you end up with a current that moves off to that offshore, that's the equatorial current. Now these main gyres, we've got the 5 main gyres in the world here, and those are essentially going to move water around the Earth in a very important way. So when we think about the effects that the Ekman transport have, and think back to our map here, we end up with a phenomenon called upwelling as well. So if we figure that if the surface currents are moving along the surface, and I guess this is a northern hemisphere map here. So as we're moving these surface currents and pushing it along the coast, the more surface water is going to move offshore 90 degrees. Well, it's a fluid, so something has to replace it. It can't just be a hole. So the deep water is going to come up in this place. This is a phenomenon called upwelling, and there's a map of upwelling zones around the world up in the upper right. Upwelling zones are really important because these bring deep water nutrients that are nutrient rich, and they're coming up often in areas where there's lots of sunlight, and nutrients plus sunlight means primary productivity. It means phytoplankton will bloom, and it means there's food for animals. So these are often some of the most productive fisheries areas in the world. Upwelling zones off of Peru are extremely important. The upwelling zones off of California are extremely important. This is an important phenomenon that is a physical phenomenon, but it is important for life on Earth. When we start to think about how this moves water around the world, and thinking back to the density conversation a little bit ago, as we think about cold water sinking, we have what's called deep water formation in the polar zones. So this is what's called the global ocean conveyor belt of water around the Earth. So there are these deep water currents that move throughout the Western Atlantic, and then they will move along the poles. These will surface in the upwelling regions and become warm water, join with warm water currents around the world, and move water around the world over thousands of years. So this is an interaction between, it's called thermohaline circulation because it's both temperature and salinity based. Remember, if you have denser water, it's going to be more saline. So we're thinking about how that temperature and salinity influences how this deep water formation happens, and there have been some papers published in the literature talking about how freshwater inputs of melting glaciers off of Greenland could shut this down, which would be very bad for movement of heat around the Earth, because this is a very important circulatory system for the movement of heat around the world. Thinking a little bit more about water circulation on a smaller scale, if we think about waves, this is produced by any kind of disruption in the surface of the Earth. We have crests and troughs. When we're thinking about measuring wavelength, it's from crest to crest or trough to trough. The wave height is from the bottom of the trough to the peak of the wave, the crest of the wave. So those are the parameters of that. If we were to consider wave frequency and wave period, these are inversely related. So essentially, if we think of the wave frequency, you've probably heard of hertz before, which is all it is 1 wave per second. So if we have 1 hertz, we would have 1 wave per second. Now, that would mean that there would be 1 second for every wave, which is the period. Now, if we have 2 waves per second, the frequency being 2 hertz, we would have a period of 0.5, which would be the time required for 1 wave to pass. So it would be half a second. So I say they're inversely related because everybody can do 1/2 in their head. And if we think about how that's related to how energy is moving along, that's going to come into play here in a second. When we think again about the circulation that's happening up and down within waves, essentially, if you have this little blue particle here, it's just going to move in a circular motion. And as you go down in depth, there's less and less energy and less interaction of the waves with the water that's deeper, but there is also circular motion in the depths of the ocean. And eventually you get to a point where it's negligible, or you get to a boundary layer where there's essentially no movement. Now, as those waves start to move into shallower water, those circulatory patterns start to get compressed into ovals, and these waves start to interact with the bottom, and this crest will get higher to the point where since the interaction of those particle movement is happening with the bottom, those waves will eventually break on the shoreline. Thinking more broadly about how things move around the Earth, when we think about water circulation with respect to tides, first of all, it's not just the moon; it is also the sun. So the moon and the sun interact to create our tidal cycle. Now, when we think about spring tides, that's when we typically have a new moon or a full moon. That's when the moon is aligned with the sun, either in between us and the sun, or on the other side of the Earth, aligned with the sun. So essentially what this does is it produces a bulge on the Earth's surface. We also end up with a bulge on the other side of the Earth, directly 180 degrees because it's the inertia of that movement around the world. So the Earth is also rotating underneath this, which ends up meaning that there's both the interaction of the continents and the rotation of the Earth with this whole system. So when the other piece to think about is that, so since this does change over the course of a month, when we have a quarter moon, either a first or third quarter moon, those are going to be our less extreme tides. Spring tides are going to be the high highs and the low lows. So if we look at this over the course of half a month, if we think about the coastline, these spring tides, the highs and the lows are much more extreme. As we get to a neap tide, these are much less. So if we think about how you may see some of these abbreviations on navigational maps. Essentially, depths on navigational maps are considered mean, low water. Around the, essentially we want to make sure that you're not going to run aground. So the maps are going to be, again, here. Charts are going to show you the lowest astronomical tide so that, again, you don't end up getting a difference. But that doesn't mean that you wouldn't experience a deeper depth at those locations. These tides can have different patterns based on where we are in the world because, again, the continents are interacting with this. When we think about a semi-diurnal tide, you would have 2 highs and 2 lows during the day, and those would be approximately the same size. Now, we have semi-diurnal tides on the east coast of the United States. We have semi-diurnal tides in most of Europe and almost all of Africa. When we think about a mixed semi-diurnal tide, one of those 2 high tides is going to be higher, and one of those low tides is going to be lower than the other one. That's an example would be, within the Caribbean, along the western coast of the United States. And then a diurnal tide, which is where we have 1 high and 1 low every day. An example of that would be in the Gulf of Mexico or off the coast of Alaska. So again, in terms of how the water sloshes around the bathtub, these tides end up being really important for navigational purposes and for how we construct our coastal barriers and the like. If we were to think about tides being different heights around the world, again, the water sloshing around the bathtub and Coriolis Effect having an impact on the movement. Again, things are moving in different ways around these different lows and different highs in the world. It's an important piece to how water is moving around in circulation. So at this time, this concludes part 3, and I will catch up with you on future lectures. Thank you very much. Thanks for watching. If you'd like to support us, please go to buy coffee at www.upwellcoffee.com or go to remoteecologist.org/support to donate to our nonprofit or to join us in the field on trips. Thanks so much.